So would you guys agree that if we wait until at least maybe 6:05 Pacific, 8:05 Central before we play the video, or should we wait longer for John? What do you guys think?
I think that sounds good.
Okay, perfect.
Yeah.
Right, in that case, let me see if you guys get the audio. Hang on 1 second. Zoom.
You're on.
Okay, good morning, everyone, or wherever you are, between Seattle, which is about 6:30 in the morning, and Kigali.
Can you hear that pretty well? It works. Okay. Because what I'm not 100% sure is if this actually plays through my speakers and records again through the microphone for Zoom, or if that's somehow done internally.
Oh, are you doing the share sound?
How do you do that?
That was something I learned from Veronique. So if you share your screen,
yes,
and when you pick what it is, which screen you want to share or what object you want to share, is there at the bottom left something that clicks share sound in your menu?
Oh, yes. Oh, perfect. So I do this.
I think, yeah, let's try that.
And also maybe, okay, hold on a second.
Uh-huh.
Oh, I need to install the Zoom audio device. Okay, hold on. This will not take very long, but
okay.
Glad we tried that early. Oh, I see. Huh.
This in mid-afternoon.
How's
I'm
this?
very happy to be with you today. I'm going to discuss the theory and calculation.
Is that better?
I think it's better. It's better for me.
Okay. I can barely hear you now, but I guess we'll roll with that.
Oh, you can barely hear me now because of your Zoom settings?
It did something with my sound, I suppose, but that's okay.
John is online now.
Oh, perfect. That's even better.
Hi, Andre.
Hello, John.
This is Michel, actually. But
oh, sorry, I can't. Oh, here, now I fixed it. Right? Sorry, my sound is back. Yes, I can hear and see you now. Hey.
But just to mention, I was hearing well, but I couldn't see the slide very well. It was kind of like there was some black spot to it. Can you try it again?
I don't think we have to do it. John is actually here. That problem solved itself, luckily.
Good.
Hey, John.
Hi, John. Richard, should I go ahead and take a couple of photos now?
Oh.
Would that be all right? Or should we just
sure
start the talk?
Right.
Okay. All right.
Yeah, you do it whenever it's
okay. I'm going to try to take a couple of photos. I have my iPad. Oh, everybody's turning on their camera. That's great. I just want to catch people who before they take off. Hi, Yo. Very nice. Christian, I'm beginning to see you. Smile. Yes, very good. Sourire. Yes. Kisung has his camera off. Let's see. Monsieur Josue Habib. Okay, I see Emmanuel now. There's Sinead. Very nice. Nipa. I
saw Nipa's photo. Okay, yeah.
I see Dick Hartman. Very good. Nis. Okay, now we smile. There's Steve. Miss Finn is there. He looks serious. Michel Cote has there we are. There's Nita. Very good. Tuna. Very good. Okay, let me make to another group. Okay, there's Andre. Perfect. Richard is smiling. Javier looks very serious and like a rock star. Renata's there. Who else? I see Georgies, I've been mispronouncing your name, I think, for 4 months now. I'm sorry. I'm sorry about that. Okay. Georgies. So it's a hard G. Georgies.
Yeah, Georgies.
Georgies. Okay. Yes. I've been saying George, so Georgies. Okay. Kisung is there. It's probably dinner time for Kisung in Korea. Okay, Asnake, I don't see your camera. Where's Omalolu? I don't see Omo. There's John. He's a bit closer. That's good. Joining us from the coast. And let's see. Very good. Okay, thank you so much. I'm going to do that again later, and it will be okay. The same. All right. Sorry, John, to
Thank you.
take time into your presentation. I will go away now.
Okay, great. So we can probably get started then. Welcome, everyone. My name is Andre Schleifer. I'm from the University of Illinois, and it's my pleasure to be part of this great event. Just for housekeeping, I guess the first talk will be given by John Rehr. John, you have 30 minutes, and we'll leave some time for discussion. I think we'll just add the time that we started later to your total time, so that's fine. John is from the University of Washington. He'll present on theory and calculations of excited state electronic structure and X-ray spectra. John, so if you could share your slides and then just take it from here. And you're muted still, John. I think we see you talking.
He's trying to get things going, it looks like.
We still cannot hear you, John. I don't know if you can hear us.
Okay.
There you.
I think I'm unmuted.
Yep, perfect.
Okay. I need to still set something up. So give me a couple seconds.
No problem. Looks like you're in very nice weather, at least.
Yes, I'm actually in Weiser, Idaho.
Oh.
At a music camp that temporarily, because I wasn't sure about. There we go. This is much better. Okay.
We may have lost the audio again.
Lost audio again?
There you are. All good.
Oh.
Okay. Just a second. Is that too bright?
I mean, not for us, I suppose.
No.
Just. They have a funny internet connection here. And so I have to be in a place that was a little unusual. So, okay, let's try this. I may still have too bright sun. Is it okay?
Yep, for us, it's okay.
Okay, so now I have to find my talk, share screen.
Okay.
Yeah. Let's see the screen. And hopefully you will be able to see my talk.
Yeah, we see currently your entire desktop and the presentation. Yep, that looks great. Okay. Thank you so much, John. You can take it from here.
Okay. Well, good morning, everyone, wherever you are. I'm happy to be here, or at least virtually. And you see my talk, Theory and Calculations of X-ray Spectra and Excited State Electronic Structure. My talk has three parts. I'll start, of course, with an introduction and how excited state electronic structure is connected with X-ray spectroscopy. Then a kind of review of what we call a quasi-particle theory, which is an independent particle approach. And finally, what we call a full theory that includes more many-body effects, inelastic losses, and many-body excitations. So I start always with a quote. Actually, I have two quotes. This is from our hero, Richard Feynman. What he always said was that if he couldn't calculate it, he didn't understand it. I think that's very true. So what we've tried to do is develop a quantitative theory that can be compared with high performance accurate experiments. Actually, it was the other way around. The experiments came first, and the challenge was to match them. The second thing that I remember him saying was that if a theory is not really one of these fashionable, high-profile things, who's going to actually take the time to find it? So anyway, one sometimes finds oneself in a small niche that's not well populated. This is one of those areas that kind of takes a long time to develop. Okay, well, what's the challenge? The challenge is to work on a theory that can be compared with experiment over a very broad range of energy and time and space and distance scales. So it's you can't be comfortable within one order of magnitude. So for electronic structure, we need to have a theory that can span 10,000 electron volts. That's the range of electronic energies going from a deep core to a photoelectron of several thousand volts. And if one measures X-ray absorption by passing an X-ray through a material, you see that that absorption coefficient also goes through about 10 orders of magnitude over a scale of 1 to 10,000 volts from the visible ultraviolet region around 1 eV to hard X-rays at 10,000 eV. There are lots of jumps along the way, but what you see near each of these jumps, which are called X-ray edges, you see a lot of oscillatory structure. That's called fine structure. In the old days, it was called XAFs, and the challenge was to explain that, because it turns out that the wiggles are directly related to properties of a material, mainly their coordination numbers and interatomic distances. So this is used as an X-ray microscope. Anyway, the challenge they gave me was to try to calculate this, because otherwise you have to calibrate with the material, and the calibration was difficult. Okay, well, where do excited states come in? Well, when we first started this, I was working with the guy at Los Alamos, Robert Albers, and he had an LAPW code, an early one, and so we tried it out. We tried this out on copper because they had very good experimental measurement. And the edge there is about 9,600 electron volts. And you can see this fine structure that goes out for about 1,000 volts. And he had to take a whole bunch of panels of this LAPW code to get this Milli-Rydberg spacing and so on. But the results were a little disappointing. Although the agreement was pretty good in the first 10 or 20 EV, it got progressively worse as we went along. The DFT got way too big fine structures, and the wiggles were at slightly wrong places compared to experiment. Now, I've also shown to foreshadow what I'm talking about a theory that has electronic structure, excited state electronic structure in it. Anyway, the takeaway here is the experiment exhibits strong damping that's not usually in DFT, which is treats electrons as real particles with delta function like spectra at the various energies, epsilon K, block energy. Okay, well, also at about the same time, and I realized this is 50 years ago now, some experimental scientists developed a theory for this fine structure. It was oscillatory, and so it was expressed in terms of some oscillatory functions, just sine waves. And what you see is that the sine waves involve the near neighbor distance. K is the wave number of the photoelectron, square root of energy. But you see that there were several effects in this equation that couldn't be described by DFT. One is the mean free path, lambda, of the electron. And that turns out to be pretty short, 5 to 20 angstroms. So this is a kind of short range order theory. There's some vibrational effects. This is a Debye-Waller factor you might find familiar from X-ray scattering. It has the same form, but slightly different mean square vibration. Also, there were these phase shifts, and the phase shifts alter the distances that you would get if you simply did a Fourier transform. And one would love to calculate that object. Then there was a many-body amplitude factor out in front and some scattering factors. Anyway, it was a kind of complicated formula, even though you want to get distances out and coordination numbers. The sums over all the different distances between the things. The energy range is very large. Okay, well, when you try to start calculating X-ray spectra or optical spectra or many other physical quantities, the starting point is usually Fermi's golden rule. It's a beautiful equation. So what we have here is an equation for X-ray absorption. I call it mu as a function of energy. And it's given by a sum over all the final states in the system, because you're making transitions from an initial core level to a final state, mediated by a transition operator. This is a dipole operator for simplicity. And then there's an energy conserving delta function. This is called a sum over states formula. It turns out to be computationally intractable because there are too many states if you go up to 10,000 EV. So first you have to solve the Schrodinger equation, calculate all these states, calculate all their eigenvalues, and then do this sum. You can get away with it maybe at low energies, first 10 EV, and that's what band structure codes do extremely well. But we needed a different paradigm. And what turns out to be very convenient, theoretically, is to use Green's function. The Green's function is a little different than the wave function. I've shown here the resolvent form. The Green's function is the inverse of E minus H minus sigma, where the quantity sigma is called the self-energy, cursive. And this replaces the exchange correlation functional and density functional theory. It's energy dependent. Anyway, this is our motto, no wave function. See if we can get a theory that's like no wave function. I'm sure you'll all appreciate that. In any case, the beauty of the theory is that instead of summing over all these final states, the absorption coefficient is given by a single matrix element of the Green's function for each edge. Well, it's non-local, so this is 7-dimensional object, but in any case, it's still a single matrix element. So the wave functions are implicit in this quantity. The quantity H is the Hartree or Hartree-Fock Hamiltonian, and sigma then is this additional self-energy that contains all the many-body effects. So what's a Green's function? Just to review for everyone, you all remember the wave functions, the solution of the Schrodinger equation, H psi equals E psi, and psi we say is the amplitude to find a particle displacing an electron at some point. Okay, and in DFT, the many body effects are in the exchange correlation. So this we know in our sleep. Green's functions are actually quite similar. They almost solve the Schrodinger equation, but it's an inhomogeneous one. H minus EG is a delta function, and this delta function is kind of the point of origin. So the Green's function is what Feynman called the propagator, and it's the amplitude for a particle to propagate from a single point. In our case, it's where the photoelectron was created in the deep core orbital to some point R prime. And the many body effects are in this energy-dependent self-energy. So for details, I strongly recommend this wonderful book by Richard Martin, Lucia Reining, and David Sepperly. It's called Interacting Electrons. It has everything you wanted to know about many body theory. And maybe you all know this from previous workshops. But if not, go out and get it. Okay, so what's the interpretation? This is a kind of quasi-particle interpretation. We have to switch gears. Electrons don't have a single energy, but they have a spread of energies. They're mostly located at a rather sharply defined energy. The independent particle position may be slightly shifted. And at low energies, they have a very narrow width. This is the range where DFT works quite well. But as you go up in energy, and as you can see, I've gone up in units of the Fermi energy to 5 or so. What you see is that this quasi-particle peak broadens and keeps broadening. And what happens is that as the many body effects turn on, as you go up in energy, you start losing energy because the photoelectron is creating other excitations. And this so-called spectral function gets satellites. The satellites appear when there's enough energy to create a kind of plasmon excitation or other kind of charge transfer excitation in the material. So that's what's happening. So our physical ingredients are this spectral function, A, that describes the energy distribution of the electron, and the width of the peak is our mean free path. It's very long. At threshold, it gets shorter and shorter as we get up in energy. Okay, so how do we calculate the Green's function? It turns out there's a very nice formalism. It's basically treating the Green's function in real space, the way Feynman pictured it, in terms of a propagator. And this is a review article that I wrote with my colleague Bob Albers at Los Alamos, where we did this early work. One of the nice things about the Green's function approach is that energy appears as a parameter. You know, we got rid of the eigenvalues. They're implicit in this Green's function. But now we have a formula in which energy is a parameter. And that means that the theory naturally parallelizes. We can give each processor in our computer different energy, and we can calculate the whole spectrum at once if we have enough processors, or at least it parallelizes beautifully. So that's a great advantage because we now have great computers and we can calculate one of these spectra in the order of minutes. More recently, we've been able to calculate these many body effects from first principles, everything ab initio, and this more extensive theory is described in an issue of Quand Rendu, 2009. It's edited by Lucia Reining, whom I've also had the pleasure of collaborating with in the last few years in getting these many body effects properly calculated. They're all implicit in this Feynman diagram. We have a photon coming in. This is the core orbital where photoelectrons created, indicated in green. The core hole, Green's function, is represented by the black line going backwards in time. And what's really important is that this shouldn't be called the photoelectric effect. It's the photoelectric core hole effect, because there's these excitonic interactions that are crucial in getting the spectrum right. There are also these excitations that you can create as the photoelectron moves out. So this is our diagram. It represents about 100,000 lines of code in the end, but that's our challenge. Calculate that up. Okay, so what are our ingredients? Our ingredients are naturally the Green's function for the photoelectron. This is the core hole potential that's created. So that's the excitonic effect. The self-energy is due to this creation of excitations. There are these Debye-Waller factors because you have to imagine this whole diagram being averaged over interatomic distances, and they're fluctuating due to finite temperature vibration. And then there's something else called multi-electron excitations, because what you don't see is that along with this process, you can also sometimes get an extra electron coming out. And that's because the Hamiltonian changes. There are these shake-up excitations that accompany photoexcitation. How do we calculate it? Well, it turns out there's a very beautiful theory due to Lars Hedin. It's called the GW theory. You've probably heard about it, but it's a very nice approximation for the self-energy. And in an electron gas, this can be calculated with a simple so-called plasmon-hole approximation. Anyway, I recommend this, at least for getting started with GW, the plasmon-hole approximation. Turns out that for any other material, this is lithium fluoride, you can represent it as basically a sum over plasmon-fold, because the W that comes into the GW has a spread of energy. And there, you can see there's some fairly sharp energy, and the shape is due to the dispersion of the plasmon. In any case, when you do the calculation, you find that the self-energy, which is this GW, has a real part and an imaginary part. The imaginary part adds to the lifetime of the photoelectron. And if we plot it up, here's what we find. This is the real and imaginary part of the self-energy. Over the first 10 eV, it's pretty small. And then, as you see, the imaginary part starts growing. The crossover is this plasmon frequency, which is, say, 10 to 20 eV. And similarly, the real part gets smaller and smaller. So this self-energy leads to shifts and damping of the spectrum, just like what I said it was going to. The core hole effect is rather strong. It turns out that what you need in the theory is a screened core hole, because you don't have a bare core hole, and actually all the other electrons in the problem see it. There are a couple ways of calculating it. We use either what's called the final state rule or RPA. They're pretty similar. There are other ad hoc methods called the half core hole that are roughly okay, but they're ad hoc approximations. So do it a couple different ways if you want to see the differences. Both of these are pretty good. How about the Debye-Waller effect? Vibrational effects can usually be calculated by the so-called Debye intervals. This hyperbolic cotangent is essentially phonon occupation number n plus a half h bar omega, and rho of omega is the phonon density of states. And what I've shown here is the phonon density of states of copper. And so what we do is we represent this by a sum over poles. We don't have to solve for all the phonons. All we need is the rough density of states, and we can calculate this quantity quite accurately by a recursion method. This Lanchos is basically a Gaussian integral over a finite number of steps. We've used the Abinet code in our calculations to get very accurate by Waller factors. So what's the result of all this? So I've shown here some magnesium silicate. This was done by Delphine Cabaret in Paris. And what I've done is I've compared the experiment, which is in red, the red dots, with DFT, with the Paratech code, and with our final state corrections, this self-energy. And so what you see is that the excited state theory shifts the spectrum from DFT to make it much more like the experiment and adds broadening. The DFT gets worse and worse after about 10 or 20 EV. So when one tries to use this fine structure to explain distances, it was really crucial that we included this self-energy in. So those are the effects. Things shift by quite a bit and dampen those effects. Basically, though, the self-energy fixes a lot of the DFT errors, although there's still some amplitude discrepancy going on. So now we're on to part 3, and the challenge is to calculate these multi-electron excitations. So what was also recognized from the very beginning, at least Ed Stern knew about it, was that the amplitudes that one gets with a single particle theory are a little too high. If you look at some transition metal oxides, you also find that there are some extra peaks. So this is the single particle theory, like from that Paratech code or RFF code. And if you look about 10 volts past the edge, compared to experiment, you see there's a missing peak. Embarrassing, isn't it? And also the main peak is a little too large. What the French group did, and this is Christian Rehr and Calandra, they did an ad hoc convolution of the XPS spectrum and the X-ray absorption spectrum, because they knew that the XPS spectrum measures the excitation energy in a material. And as you can see, this does the trick, this particular convolution. It puts in a peak just where you want it, and it reduces the size of the main peak. Very nice. So where did this thing come from? Well, if you go back to the Feynman diagram, what you realize is that we didn't write down all the diagrams. We should have realized that the suddenly turned on core hole can also create excitation. So we need to add to the theory the core hole Green's function. This has been termed the source of the intrinsic losses, the losses that you get just from suddenly turning on a core hole. And they're described by the core Green's function. So when we do that, we now have a two-particle theory. It's a photoelectron hole theory. And instead of our quasi-particle approach, we have a spectral function that's now particle hole-like. And this spectral function has the core hole in. So bingo, we have the Calandra et al. Convolution formula. This spectral function is essentially the what's measured in XPS. They measure the core hole Green's function, apart from some matrix elements that are relatively smooth. how do we calculate the four-Green's function? We've used a technique which is again different from the conventional one. The conventional technique is to use the Dyson equation. G is G0 plus
Uh-oh. We may have lost John.
and it's a
I think he's gone for a second. I think his internet broke down. Let me see. Is he still on the? Okay, John, can you hear us? I think. Oh, I think you're rejoined, but you're muted again. I'm sorry.
here we
Okay.
go.
Yep.
How's that?
I think that's good. And if your screen share also dropped, I don't know if your internet went down for a moment there.
It could have gone down for a minute, just a minute.
No problem.
Let me go back. Here we go, screen share. How's that?
Perfect.
Okay,
Okay.
now I have to get back my talk. Excuse me.
So if you, and in terms of wrapping, maybe you could have like, I would say roughly maybe like 5-6 more minutes, and then we have some time for questions.
Okay, I think I'm on track.
Perfect. Okay.
Okay, so where I was trying to describe our way of calculating these multi-electron excitations. We use a cumulant form for the Green's, which all the many body effects are implicit in this so-called cumulant. The cumulant is also proportional to this GW self-energy, at least the imaginary part, and it can be described in this Landau form. Oops, I'm going back up. This is going to simplify our interpretation. As a result, it turns out that we can explain these satellites that you see quite well. What I've shown here is titania and the L edge. So there's a P3 halves and a P1 half main peak, but then there are these satellites, and the theory is capturing them pretty well. It also gives a nice real space interpretation. In this case, it's due to charge transfer excitations from the nearby oxygen ligands to the titanium D states. So you can see the P to D charge transfer behavior. One more thing I have to mention. So in addition, now we put in these intrinsic losses. There's also these interference terms. They cut down on the interference, and you need all these terms to get the particle hole spectral function and get everything right. So that's the full theory. So we have it all, at least for a lot of materials. It works pretty well. This is nickel oxide. Again, the interference terms actually turn out to be quite important in getting the behavior right at the edge. It turns out you can even do some F-electron materials, not all. The satellites take quite a bit of the oscillator strength in these materials. You can see it's maybe half. And the theory cuts down pretty well and adds these other excitations, but it's not perfect. You're probably wondering where to get the software. We have the PEF project, so I recommend that you go here. You can always email us for questions, but it can be, these have all the links. We're also associated with a theory institute for materials and energy spectroscopy. It's called TIMES. It's centered at SLAC, and we have a number of software items there. There's a collaboration with PNNL for chemical systems, and there's more software there. And finally, I should point out that the materials project has input files for the FEF code for everything in their materials project database. So that's about 100,000 systems. Okay, well, I'm at conclusions. I hope my timing is reasonable. What I've tried to show is with excited state, electronic structure is essential for a quantitative understanding of X-ray spectra. We now have an ab initio theory that can treat the full spectrum from the visible up to the X-rays. And our theory now augments the one particle effective theory, or particle Hall theory, with a spectral function. Are we there yet? Well, it would be nice to do a better job on the interference effects. There are these systems with multiplets. There's work ongoing. And then there are these very strongly correlated systems. So still a little more to do, but we have a theory that can accommodate a large number of material. So with that, I'd like to close and thank a large number of collaborators along the way. This is a partial list. In particular, my colleague Josh Cass has contributed a lot to a lot of this work, and really appreciated the work with Lucia and others. And I'd like to thank all of you for getting up early, if you're in the West Coast or wherever you are today. And I'll be happy to take any questions. So thank you all.
Okay, great. Thank you very much, John, for a great talk and an impressive amount of work. I guess at this point, I will take, of course, questions. So you guys can speak up if you want. You can also message in the chat. I will try to keep an eye on the chat. And while you're preparing this, maybe I'll start, John, off with one question, which goes actually back to the beginning of your talk when you showed this comparison between DFT and experiment, and you said there are a large number of oscillations in the DFT spectrum, and then you said it's damping that is important in experiment that dampens these oscillations. Is that how I understand this, or what gets rid of these oscillations and makes the curve so super flat, like people see in experiment?
Okay, there are two things. One is the imaginary part of the Green's function, so that's like a Lorentzian broadening that goes in. So you imagine taking an oscillatory spectrum and just broadening it out over the width of the wiggles. The wiggles will get damped. It's like an e to the minus lambda e.
But that means a very large broadening, I guess.
Absolutely, yeah. The broadening is several eV.
Right.
Okay. Secondly, there's the vibrations. The vibrations actually contribute a lot to this. So typically at about 300 Kelvin, when you get up in energy, you can really see the effect of this Debye-Waller factor. So it's maybe dominated by Debye-Waller factor in many cases. So it depends. It depends on the temperature. In platinum, you can actually get wiggles that go out quite far. The damping is less because the mass is very heavy. So you need both. Those are the two damping factors.
Oh. Okay, very interesting. It reminded me, I mean, I know it's not the reason because you just explained what the reason is, but it reminded me a lot of K-point convergence that we see in optical spectra, but it's of course a different energy range. Okay, Michelle Cote asked a question here. Michelle, you can read it out loud if you want, otherwise I'll read it.
That's okay, I can ask it.
Okay.
I'm just wondering, like, so how do these calculations scales in terms of number of atoms, and what kind of system size now is it reasonable to do?
Let's see. Well, The main calculation involves then calculating that Green's function, which is like a matrix inverse. And typically, that scales like n cubed, of course. We can do several hundred atoms, up to 1,000 atoms in, let's say, wall clock time. So, yeah, it's actually quite efficient to get this Green's function approach. Now, if you want to do all the edges, and you have a very heavy atom like plutonium, that can add. But if you restrict yourself just to the K edge, it's very fast. You can. So these are actually wall clock time. Putting in all the many body effects, of course, adds to this. So it depends on how good a job you can do. But
maybe a complement question is like, can you see the effects of correlation in the balanced electronic states, and
yes.
and things that you expect not DFT to be well represented there, and like Mott and Slater and so on?
The answer is yes. Actually, coming very soon is an extension of the materials project for calculating those optical properties. We use an approximation which is similar to RPA. It doesn't have all the excitonic effects in there. If you really want to do a good job in the optical, you need beta saltpeter code. So that's like our particle hole Green's function code. That takes gobs more time and a lot of computer resources. And it's something that our collaborator, John Vincent, is working on, and the Reining code and Claudia Drexel. So for optical, you really need a very good treatment of this particle hole phase.
Okay, so you're not like thinking of doing like DMFT or something with that. You restrict yourself to Green's function and better, but none of these corrected methods.
Actually, thank you for asking. We are exploring DMFT multiplet methods at the moment, so stay tuned.
Okay.
I haven't decided which way will work. There's actually a work by Silke Biermann on a DMFT plus cumulant that's very close to our approach. So we're working on it. I don't know what the answer is yet. Even DMFT is not easy. So this is, I would say, current work in progress.
Okay, thank you.
Great. So let me go to Dick Hartman real quick. I think he mentioned in the chat, Dick has some questions. Maybe you can also just go ahead and ask your question.
Yeah, thank you very much. So thank you for the talk. So it was a good talk. But I have, actually, I'm working in several projects using the X-ray absorption spectroscopy. And also, okay, so I would like to know if there is a way. So I have, let's say, 3 questions. So if it's possible to determine the oxidation state of, a metal through the K edge of the ligand, by looking at the K edge of the ligand, okay? If we have a system which has like, a transition metal, a transition metal atom, this multiplex effect. If you cannot deal with L2PH directly, is it possible to check through the K edge of the ligand, the oxidation state of this metal? And also, my second question is the method that you presented about Green function. Is it possible that green functions deal with multiplex effects? And also in the second, probably the third question, since I'm presenting my poster today, it will be helpful that I show you some curves that I have according to the experimental spectrum, there are some divergences in, let's say, at high energy between the theoretical spectrum and the experimental one. I would like to discuss with you more what is the origin of this divergence. So thank you.
Okay, well, you have a lot of questions there. First of all, getting the oxidation state, the way we do it is to, when we do the calculations, we look at the self-consistent charge counts on each atom. And what we found is that these charge counts are roughly proportional to the oxidation state. You get more and more charge transfer when you do this charge count, and codes like the PHEF code and maybe many others will tell you these charge counts. So when you then compare the spectrum with experiment, you can see that there's more and more charge on a given atom, and that's related to this oxidation state. The oxidation state's a kind of hand-wavy concept, not particularly accurate. But so anyway, the answer is yes. Or you can look at free-edge structure. There's a lot of techniques for getting this rough oxidation state, but we do it by actually looking at the electronic structure after we do the comparison, and that gives you a better picture of what's going on.
Okay. So just in the interest of time, I suggest I will ask Das Pamaraju's question in a second. Javier, maybe you can get ready to show your presentation. John, so the question by Das is, where does the form of the cumulant come from? Is it a heuristic guess, or is it derived explicitly from perturbation theory?
That's an interesting question. You can always define the Green function in terms of a cumulant, and it turns out that that form is exact if you have core electrons coupled to bosons. So if you make the cumulant ansatz, then you will find that form. It's not completely correct. There are these, well, you can put anything into the cumulant, but make that ansatz. It turns out that the usual form will have some nonlinear terms in there that go beyond the linear DW approximation for the cumulant. But so regarded as an ansatz, it's the link cluster theorem. That's another way of looking at it. That's the way Jerry Mann and others talked about it, or Nozier and Denominiti. It turns out that this is a beautiful form for electrons coupled to bosonic excitation. So, but it's just a mathematical equivalence based on link cluster theorem. You can always expand general series of Feynman diagrams in terms of the so-called link clusters. So, in that sense, it's a theorem, an exact representation.
Okay, great. Thanks, John. I suggest, so there are more questions I see in the chat. I suggest we delay those to the panel, and we now go on with Javier's talk. It also looks like we may have one speaker missing for the next session, so I think I'll be able to give you guys your break in a moment. But let's start with Javier, who will talk about the INC code, which is a state-of-the-art implementation of DFT. Javier, please go ahead.
Okay, well, thank you very much for the opportunity to talk here. So I'm going to talk about this INC code. That is a new DFT code we are developing at Lawrence Livermore National Laboratory. Probably most of you are familiar with density functional theory, that it's basically a method that allows us to perform quantum simulations in computers, a computational tractable way of quantum simulations, specifically for matter. DFT is, of course, a very successful method, and it's estimated that around 15% of the supercomputing time is used in DFT simulations. And of course, this comes from the success in the last 20 years or so of the, or even more, of developing DFT codes. So solving DFT is not easy because there are a lot of different components that you have to integrate, and it's also very expensive computationally. So there's a lot of development, a lot of know-how about this code. The problem is these codes are old. They were designed, they were started a long time ago. Where computers were very different, and the programming was very different. The philosophies and everything was very different. And that means that today these codes are not very efficient for modern supercomputer architectures. In particular, the fact that we are mostly using GPUs these days, and most all the new fast computers are based on GPUs, means that there is a big gap between like what the computers can do and what actually we can do, the simulations we actually can do with DFT. So this is why we started the INC project. It's something we started developing around 2 years ago. Thanks to funding we have from the basic energy sciences program of the Department of Energy in the US. And our objective, our main objective, is to have a code that can do TDDFT simulations, real-time TDDFT simulations efficiently in GPU supercomputers. And when we started this, we decided, okay, what are we going to do? Are we going to just take one of the codes, in particular the keyword code, which is what we were using at the time? Are we going to start with that code and just modify it to run on GPUs and all these things? And we decided, okay, it's better we start from scratch, and we use all these modern C++ coding techniques and all like modern strategies to develop code that have evolved a lot in the last decade or so. So we can have a code that it's new, and at the end it's going to be much more efficient, much easy maintainable and everything. So that's why how INC was born. So what are the main features of INC? Well, it's a clean design. We started from scratch, writing the code, and we managed to have a fairly complete implementation of DFT and TDFT in only 12,000 lines of code. This is thanks to all these modern techniques. So we have code that is really simple and that really has the equations and not has extra kind of ugliness because of the implementation of it. And also we started from scratch thinking about how to write a code that is parallel both in GPUs and MPIs. So all the code runs on GPU and is designed to do that. In terms of simulation, it's a fairly standard code. We use plane waves as pseudo potentials. Like many of the typical codes, we don't do something very different here. We use some of the techniques that are also used in real space DFT, but we are not very innovative for the moment in this part. The idea is to have a solid foundation we can then start building upon with like tried components we can start. And something very important for the code is that we use a lot of testing. We have tests for all the components in the code. Each component we have, we write tests for them, so we make sure that everything works properly. And in fact, the code itself has 12,000 lines of code, and on top of that, we have 6,000 lines of tests. So 1/3 of the code is essentially the tests, like make sure that this other part is working. That means development is in fact very fast because we are sure things are working and we don't have to go back and start finding bugs and realizing, oh, okay, this thing is not working. And we have, in general, we try to make the code very modular and extensible. So we divide all the parts of the code in different components that interact with themselves, but they are independent. So we don't have to work with these very big pieces of code that are kind of all interlinked. In fact, one of the things about modularity in INC is that we think in a different way of a traditional code. So probably if you are using an electronic structure code, you will know you have the code that is written in Fortran, C, or C++ that you have to go and compile. And then to use the code, you have to write a certain input file in some arbitrary format that is different for each code. And sometimes they're not very friendly. Sometimes you have to look at tables to get numbers and things like that. And on top of that, sometimes you want to do like several calculations, repeat some calculations, change parameters. So you end up writing a script that somehow generates these input files. And you end up with all this mixture of codes. And then if you want to modify somehow the code, you have to go back and change something here. The idea in Ink is different. Ink, in terms of code, is a library. It's a C++ library. And when you write a program in Ink, you just write a C++ program that uses Ink. This makes things much more, even though you have to learn the C++ language, you write C++ that may be a bit harder than this simple format. In the long run, it has several advantages. First, if you want to do some more complicated stuff, for example, explore parameters or something, you can do directly here. And the other advantage is that there is a continuum. If you want to explore lower level things, you can start going down the level with the Ink library. You don't have to really just kind of start modifying this code from scratch in a different language. So, for example, this will be an Ink input file. This is an example. This will be a C++ code. I omitted for like reasons of space all the typical things, but this is the typical begin and the main function, everything. But essentially, this will be the calculation. First, we define a distance where we can decide what units we want that distance. Then we generate the coordinates that we put in a container, a C++ container. And then we create two systems, two variables. One is the ions, and other variable is the electrons that contain information of these two subsystems. And then we call this functional thing that calculates the ground state, and we pass the ions, the electrons, and we say, okay, what is the interaction for electrons? In this case, PV. And when you get our result, when we ask the result, okay, for example, let's print what the total energy of the calculation is. And so this is a code you can compile and run, and this will be how you interact with it as a library. So as this is a new code, one of the important things we have to do first is make sure that it's giving the proper results. So with some validation work, in this case it was Das Pemarayu that did this work validating, and we found that there is an excellent agreement with both for the ground state calculations and the DFT calculations with other codes, in particular Quantum Espresso and Octopus. And of course, our main objective is to have a code that is very efficient. We're still working on that, but we can see already that the code is quite efficient, and we can scale up to reasonably well up to a lot of 64 GPUs for a system of 650 atoms. But this is getting better. In fact, I had better numbers, but our supercomputer was shut down because of the heat. The power went down, so I couldn't access it to get better data. But we're working on this, but we're already kind of getting nice results. So in conclusion, I hope you see that Ink is not your standard electronic structure. We're trying different paradigms and thinking in a different way that this normally has been done. And one of these is you have to learn just one language that allows you to go from just writing a basic calculation, do more sophisticated stuff or some data analysis and stuff like that, or even get into the code and start saying, okay, I want to implement this new feature, I want to try this idea or something. The idea is to make it accessible for everybody. Of course, it's a work in progress. There are a lot of features we still want to implement, and we are working a lot on this. The code is moving fast. And if you're interested, we just submitted our first paper. You can find a preprint here in the archive. And the take-home message we want you to consider is that we want to make this a code that is for the community. It's not a code we are going to develop and nobody else can touch. We are releasing it under a free software license, an open source license, so anybody can access the code and modify it. And it's available now. You can find all the versions, all the development is happening here in GitLab. So if you're interested in contributing or using it or whatever, we are happy for you to get involved. Well, yeah, that's all I have. Thank you very much for your attention.
Great. Javier, thank you so much for a great talk. This is very interesting. And just in this case, we'll do the question in the panel. So I think we'll delay all the questions until then. And we'll move directly to Robert Stasio's talk. And I'll let you guys do the slide switching. And Robert will present on enabling linear scaling exact exchange for heterogeneous systems. Robert, you can take it from here. I think you're still muted. Okay, perfect.
Can you see my screen okay? Can you hear me okay?
Both is great, yep.
Thank you so much. Thanks, guys. Thanks to the organizers for the opportunity to speak today. And thanks for organizing this great workshop. I'm going to talk to you a little bit about how we're enabling sort of next generation versions of our linear scaling exact exchange code for dealing with heterogeneous systems. Right, so thanks to Javier for the introduction to sort of DFT. I'll just mention, and I'm sure most of you are familiar with, the Jacob's ladder idea, this sort of semi-systematic way of improving density functional theory introduced by John Purdue almost 20 years ago, where we target the exchange correlation energy. And of course, we climb up this ladder. As you do so, the computational costs sort of increases tremendously, as well as the sophistication of the functional. But oftentimes, we hope, in particular, if it's used correctly, right, you get better and more accurate, more transferable results. So what I'm going to talk to you today about is how we're enabling sort of fourth rung functionals, right, these hybrid functionals. We're also doing a little bit on range separated hybrids, but I won't tell you about that today. So hybrid functionals, and of course, we can add on some sort of Fonderwald's correction in an attempt to try and climb up the ladder even more. All right, so the main issue though is really the cost, right? And again, I would just mention that these hybrid functionals are really important, and we're seeing this more and more, especially when you have bond breaking and bond formation, as well as things as simple as hydrogen bonds, right? Like hybrid functional makes a big difference in the modeling of liquid water. Now, the big problem is in the condensed phase, it's a cubic scaling problem. And I'll show you the equation. Here's a simplified version of it in the middle. You have to sum over all occupied orbitals or bands. And then what you need to do is an integral over all space of the density. This here is a sort of orbital density, where it's the product of two orbitals, two occupied orbitals, and the potential that you would feel from those orbitals. So now the way we tackle this is we localize the orbitals, and by localizing the orbitals, it allows us to do two tricks, which takes it from this sort of cubic scaling algorithm to a linear scaling algorithm, and that's depicted in this box. So we localize the orbitals, and the first thing is, since they're localized, you form a localized orbital product, or orbital product density rather, and this thing has a local support or a compact support. So that has a couple of consequences. The fact that the first thing is that since they're localized, not all orbitals will overlap. So I can now truncate that sum over all occupied orbital pairs and just account for the orbitals that are around a given orbital, right? Those that are overlapping. And of course, this is the key to doing everything in real space with localized orbitals. The second thing is, if you look at this integral, while the potential that you would feel from a product density is not negligible or does not have a local or compact support, right? It could go as bad as 1 over R, right? So Coulombic type potential. The product density, this rho ij, does have a local support. So when I evaluate this integral, in particular for the energy here, I don't have to do an integral over the entire domain. I just have to do an integral over the domain where the two orbitals overlap. And with those two key approximations or implementations, and of course with a massively parallel MPI OpenMP implementation, we're also doing GPUs. We have a NESAP allocation from DOE at the moment. You can really hammer this down to linear scaling. And already it's enabled us to do some cool applications. This is work that I started with as a postdoc with Roberto Carr. Here's just a small app that I'm showing here. I'm not going to get into the details, but we use this algorithm to really solve a century-old puzzle involving the different diffusion rates for hydroxide and hydronium in aqueous systems, right? And it's not until you get to a hybrid functional with the van der Waals correction or dispersion correction do you really start to describe a system like hydroxide diffusion correctly. Now, what does it mean in terms of a system like liquid water? How fast can this go? Here's some timings, but I want to move away from this and show you what we're doing now. So this is the alpha version. Here I have some scaling plots. Let's just focus on water 256. So we're able to do pretty large calculations. Water 256 is 750 or so atoms, and here's the scaling line as you increase the number of processors or MPI processes. And you see, so a nice number that I like to throw, of course, we're coming off the ideal scaling line, and I'll talk about that in a moment, but we can do all the energy and forces for the hybrid part, I should say the exact exchange part, for something like water 256 in a little less than 2.5 seconds. And that's on Blue Gene Q, which is not exactly the fastest computer. Now, if you look at these lines, and I should also mention, everything here is being done very, very accurately, right? There's no real approximation here as long as you are using tight enough cutoffs, which I'll talk about in a moment. So the error that we're getting when we're evaluating the energy and forces for the system is less than a fraction of a percent, right? Sort of on the order of 0.01 or 0.02%. Now, if you stare at these, you see the pie chart. And when I first saw this, I got very upset because if you look at this pie chart, it shows us the computational time that we're actually using. And this is sort of, you see it everywhere. It's about a third computation, it's about a third communication, and about a third idling. And that's really disappointing, but it offers also an opportunity for hammering all three. And we have a lot of efforts for doing all three of those, which I won't have time to tell you about today. So we should be able to get this back on that line or darn close by hammering with a three-pronged strategy. And I should say also that between these two papers in JCTC last year and this year, we can do not only sort of NDE and MVT dynamics or ensemble, but we can also do constant pressure, which is kind of cool, right? But we can do that also with linear scaling. Again, I won't have time to tell you about that today, but you can check out this paper. All right, so how do we do it? So to get into the weeds for a second, and then I want to show you some of our new stuff. We do there's two parameters. The first thing is we use a radial overlap criterion for determining pairs. Now, this is great for homogeneous systems. You see here, we have pictures of the localized orbitals being very spherical. And you can see if I'm sitting on the red orbital, I'm overlapping with the blue, and all you need is a radius, and it works out great. But what happens when the pairs or the orbitals are anisotropic? Like the sort of things you have in heterogeneous systems, multi-phase, multi-component systems. Now a radial cutoff is not so good, right? Here, I would think that I'm overlapping with the black when I'm not, and I'm missing the blue. So this is the first problem in the alpha version. Again, works very well for things like liquid water, but not so great for other systems, and I'm going to show you that in a moment. The other thing that we did is we use a fixed size spherical domain. So for orbitals that are close together, you need a larger domain. And as long as I solve the Poisson's equation on a large enough domain, I will get this pair exact. But when the pairs are further apart, I'm sort of using that same domain. So you're forced into a compromise. You're either, if you choose the domain too small, you're inefficient or you're inaccurate for large overlap. But then if you choose it too large, you're then inefficient because you're solving a Poisson's equation on a huge domain. Really what you want is something that overlaps just where you need to overlap. Right. So again, anisotropic and heterogeneous systems will force you to choose between accuracy and efficiency, because if I use a large radial overlap criterion in a large domain, I have to do a lot more work, and I'll get a great accurate answer, but then it's very, very costly. Right. So how are we dealing with this? So the first thing we're doing is we are using a Lebesgue integral based bounding box search. So what this does is it sits on every orbital and finds a tight axis aligned bounding box, like a parallelepiped in 3D, and that encompasses the orbital. And we did do this based off a very physically intuitive user-defined coverage threshold, right? If you integrate the square of the orbital, you should get 1, and we'll lose some electron, right? And if you choose epsilon intelligently, right, and don't get too crazy, something like on the order of 10 to the minus 4, you get errors in the exact exchange energy and forces that are, again, 0.01%. And I'm going to use that throughout this talk. And so this is the starting point, and this will intrinsically account for anisotropy in each MLWF. Some are tighter, some are more extended, and I will mention that in a moment. And I should mention MLWFs. This is one localized form of the orbitals that we use. There are others that we can use, of course. All right, so that's the first part. Now, based off of that, we now replace this sort of spherical domain, these fixed size spherical domains, with non-variable size and non-spherical domains. So we find when the bounding box overlap, and now we solve Poisson's equation where we need to. So pairs that are close together get solved more accurately. Well, I should say they're all solved exactly, right? Or numerically exactly. It's just that ones that are closer, you need a larger box, and ones that are further, you need a smaller box. Now, by doing these reduced domains, and of course, moving everything from a sphere to a cube or a parallelepiped is really tremendous for modern, sort of like Javier was just talking about, right? We need to start thinking about modern day architectures, right? This is much better for GPUs, much better for vectorized code, right? Because you don't have any logic, right? It's all unit stride, sequential memory access, right? You can bang these out, with matrix multiplications or matrix vector multiplications. And again, Robert, we don't have to sacrifice any accuracy.
Right? Robert, could I gently ease you towards wrapping up?
Sure. I'm just going to give you a couple of examples.
Okay.
So here's a so-called homogeneous system, which is liquid water. You have two types of, bonding pair and lone pairs. But if you do things with the beta version, you'll see, I should say, if you do things in the alpha version, you have to choose, these sort of size domains, one for the self and one for the non-self pairs. But if you do things with the beta version, even in a system that's fairly homogeneous, you get a speed up of about a factor of 6, right? And again, this is from the heterogeneity in the overlap domain size and shape. Now let's look at something that's a little bit more interesting. This is a bipolaron system from a metal doped molten salt in potassium chloride. Here now you have sort of normal, very localized MLWFs, but you have one MLWF that's very, very delocalized. So this guy's going to overlap with all types of pairs throughout the entire cell. And now if you try to run this with the alpha version, you don't get good results unless you start really amping up the domain sizes that you are using. And in this case, to get the sort of same accuracy, you get a factor of 30 by using our new version, because again, the pairs that need to be treated properly with large domains are done so. Everything else is treated with small domains. So take a third example would be titanium dioxide sort of rutile water interface. So this is a multi-phase, multi-component system. Again, here you don't have a lot of homogeneity in the MLWFs, but you have a lot of homogeneity because of the system, right? You have changes in the density, you have the surface states. And again, if you want to use the alpha version, you have to really pump up all the criteria. And if you do that, you'll get a very accurate answer, but you do so at a high cost. Using the beta version, you can get on the order of 0.01% error, but with a speed up of about 15x. So just concluding, right, I told you just briefly about our EXX alpha and beta versions. These are all in Quantum Espresso. Beta is not quite in Quantum Espresso yet, but alpha is. And I showed you 3 examples where we're really making a difference in terms of that time and not sacrificing accuracy. I haven't told you about, we're also optimizing it with that 3-pronged algorithmic strategy to hammer computation, communication, and idling. And again, that once we're done, we'll put that into Quantum Espresso. I'd like to thank these folks and of course you guys for your attention and the opportunity to speak today.
Excellent. Thank you so much, Robert, for a great talk. This was interesting. Same with Javier. We'll take all your, I see already questions for you here in the chat. We'll take them in the panel just after the next presentation. And the next presentation will be given by Georgies Alene Asres, and he'll be talking about promising photocatalytic and photovoltaic performance and electronic properties of van der Waals heterostructures of zinc oxide and molybdenum, tungsten, sulfur, selenium. Georgies, take it from here, please.
Okay, thank you. My screen is...
Yep, screen looks good and we can hear you.
Okay, thank you. Thank you, organizers, for this opportunity to talk and for the nice workshop. My talk is on promising photocatalytic and photovoltaic performance and electronic properties of van der Waals heterostructure of zinc oxide WSSE genus. These are my research collaborators. I think on Tuesday present by Elizabeth, so you know her. She is from UC Berkeley. Dr. Takaling is from Jeonju University, Korea, and myself, and our MSc student in Addis Ababa Institute of Technology, Girma Mokonnan. So the outline of my talk is introduction. I will discuss some basic mechanism of photocatalytic water splitting, then some results and conclusion. Introduction. In recent years, much attention has been focused on energy shortage. One alternative that has attracted significant interest is hydrogen. Currently, hydrogen is mainly produced from fossil fuels such as natural gas by steam reforming. In this process, fossil fuels are consumed and carbon dioxide is emitted. Hydrogen has to be produced from water using natural energy such as sunlight if one thinks energy and environment issues. There are several ways for solar hydrogen production. One is electrolysis of water using solar cell or hydroelectric power generation. The second is reforming of biomass, and third, photocatalytic or photochemical water splitting. So today I will talk about photocatalytic water splitting. Water splitting, you have a water and the catalyst, then you eliminate it with a light, HV, then it will be splitted to H2 and oxygen molecule. H2 is a clean fuel and oxygen can be used for water purification, water and air purification. The energy source is photon, so it is renewable, environmental friendly, and economic. So photocatalytic water splitting has the simplicity of using a catalyst and the sunlight to produce hydrogen out of water. This is a simple process for photocatalytic activity. First, sunlight or a light comes, and then photon observation. Because of photon observation, there will be electron and hole generation. The second process is charge separation and migration to the surface. After that, at the surface, there will be a reaction and hydrogen evolution and oxygen evolution occurs. This is a principle of, on the right side, a principle of semiconductor photocatalytic material. You have a valence band and the conduction band and the band gap. The two important things is the width of the band gap and the position of the position of the conduction band and the valence band. So the conduction band level should be more negative than the redox potential of H plus to H2, and it should be more positive than the redox potential of O to H2O. In this case, we can split the water, we will have enough potential, and we will produce hydrogen. What is the motivation of this work? So numerous researchers had extensively studied water splitting using semiconductor photoelectrodes and photocatalysis since the finding. However, efficient material for water splitting into H2 and O2 under visible light irradiation had not been found. And the band gap of visible light-driven photocatalysts should be narrower than 3 electron volts. Therefore, suitable band engineering is necessary for the design of photocatalysts with visible light response. Vertical stacking of two-dimensional materials into layer van der Waals heterostructures are recently considered as a promising candidate for photocatalytic and optoelectronic devices because they combine the advantage of both the individual 2D materials. The methods we have used: Quantum Espresso, VASP, and Materials Studio. This is the calculation details for the structure relaxation, and on the right side, the band edge and band structure calculation details. So first, what we have done is 8 favorable high symmetry stacking sequences we prepared. You can see on the right side, A1, A1, A2, and so on, 8 stacking. After we did the 8 stacking, we calculate the binding energy. So from the binding energy, we selected the minimum binding energies, like minus 2.75 e raised to 0.1 and so on. So we selected 3 heterostructures out of 8 structures, and this is AB1S, this is AB1SE, AB2SE. SE means the SE is facing the zinc oxide. The zinc oxide is on top, and on the bottom we have the Janus material. And when selenium is facing the zinc oxide, we say it AB1SE. When S is facing it, we say it AB1S. Then we calculated the band structure and try to evaluate it. So you can see the band structure. It is a direct band gap material at 0 strain, but we have checked it at tensile strain and compressive strain. And when we have a compressive strain, you can see that the material changes to type 2 band gap alignment. That means the top of the valence band and the bottom of the conduction band are from 2 different compounds. So we have type 2 band gap alignment, and this alignment is very good for photo-generated carrier separation, easy separation. This is the band structure for AB1SE heterostructure, and you can see it is direct band gap at 0 strain. But when we apply compressive strain of -5, it changes to the indirect band gap. Again, this is a AB2SE band structure, and it becomes indirect band gap when we apply compressive strain. It seems what matter is not the alignment, instead which chalcogenide is facing the zinc oxide from this result. This is a relationship between band structure of the heterostructure and redox potential for water splitting. So we have calculated the band positions for different strain values for the 3 different structures. In all cases, when the tensile strain increases, the conduction band position becomes more negative and it pushes down the hydrogen evolution reaction redox potential. From this result, we have seen that when we increase tensile strain, its performance for photocatalytic application is degrading. So it is better to apply negative compressive strain or to leave it at 0 strain. This is the power conversion efficiency versus the strain calculation. We have used this expression for the power conversion efficiency calculation. And for this calculation, for the fill factor, we have used 0.57. And for the energy loss, we have used 0.3 EV. We have seen from experimental literatures, this is a value used for transition metal dichalcogenides, the only paper we found, so we use that one. Then after putting together everything here, we calculated the power conversion efficiency. So from the plot, you can see the tensile strain increases the PCE more effectively than the applying compressive strain. As the tensile strain increases, the band gap decreases, so we can harvest more visible light, so the PCE increases. If we target both application, I showed you photocatalytic application, now this is for photovoltaic. If we target both of them, there is a trade-off when we apply tensile strain, and performance could be optimized by applying a small amount of tensile strain, but not too much. So my conclusion, we have explored the electronic, photocatalytic, and photovoltaic properties of van der Waals heterostructure of the zinc oxide and WSSE by first principle calculation. Models reveal that type of alignment and band gap of the bands are different for different stacking. And we have seen also change of strain has some effect on the band structure, as I showed. The band edge position of the heterostructure relative to the standard reduction and oxidation potential for water splitting at pH 0 is displayed, and we have seen at 0 strain and negative strain, it is okay for photocatalytic application, but when we increase the tensile strain, it degrades its performance. The power conversion efficiency value is calculated for 3 most stable configurations. Tensile strain increases the PCE more effectively. Even we have reached up about 20% efficiency with this calculation, so it is a good material for photovoltaic application. For future work, we are planning to see the effect of the electric field and ab initio molecular dynamic simulation to investigate the thermal stability of the heterostructure. So this work is, we started collaboration after APS March meeting by meeting with Elizabeth. Then after that, we have done this work by collaboration and we are continuing the work. Thank you for your attention.
Okay, great, Georgies. Thank you so much for a great talk. So now, as far as I can tell, our 4th speaker is not here. So I think we'll wrap it up at this point and we'll transition to the panel where now everyone can ask really anyone, but especially the 3 short talks, any questions. And so while you guys gather your thoughts, I will take a look at the chat here and see what's not answered yet. So Robert, I think you answered most of your questions. Let me ask one question to Javier while everyone else is trying to figure out what question to ask. Javier, so you said when you're preparing a simulation, you're using essentially C++. Now, learning the language is one thing, but you also have to learn the ink code in its inner workings, right? To really use, the right function at the right part of the code at the right place. Is that true?
Yeah, but the idea, I mean, at the end it's the same if you're, for example, you're learning, I don't know, quantum espresso or Avenir, whatever. You have to learn how to do certain things. So that's more or less the same level of.
Yeah.
So we try to make a simple interface, but so it's so the code is kind of so the idea is that maybe a bit more difficult, but not much more difficult than learning like
any other code.
Yeah, and the other advantage is what we think is a big difference is when you want to parse the output, because different codes have some things like crazy output formats and kind of you want to parse the wave functions of a code and it's a nightmare, different format, and you have to figure out how it is, and it's usually not documented and stuff. Well, we think you will have just an array with the data, so that will be much more easy to do.
Right. You could even do some post-processing directly yourself if you wanted to, right?
Yeah, exactly. And the idea is, for example, let's say you want to calculate the gradient of the wave functions for some reason.
Yeah.
Ink will give you a function called gradient, and you just can do that directly instead of having to, okay, load the coefficients and then I calculate the gradient.
Right. Interesting. Okay. So let's see. Anyone who has a question, wants to just speak up, please go ahead. In the meantime, I'll try to dig through the chat and see what has not been answered yet. And anyone can ask any of the speakers.
Okay, sorry. Gamakis, go ahead.
Go ahead, Gamakis.
For the chance, I appreciate all the great talks. It's very interesting. So I have one question for Robert and actually suggestion, or I need some comments from them to direct us. For Robert and for Johan, really what they presented for us is beyond my understanding, because maybe after some years I may understand that. But would you please give us some clue or hint how to do this excited state or many-body perturbation theory calculation with limited resources? Actually, forget it not that I am from Africa. I have limited resources. I wanted to do this calculation. So what shall I do? Please comment us, give us some direction to do with the resource I have at hand. Thank you very much.
Do you want me to respond?
Yep.
Okay. Well, the good news is that we have embedded this theory in codes that are very efficient. The Green's function approach is quite efficient. And so you can basically apply this to any material, at least any material in the materials project. And so we have simplified the process. We have all the input files. It basically amounts to running the code, and you can learn by doing. You can do a lot of examples. So the code is actually fairly, I would say, user-friendly, and it has both novice and expert levels. So it's relatively easy to get started. We've tried to make it easy for beginners, and I think it's possible.
And I follow up. Do you need a big computer?
Not really. You can do most of these things on your laptop. If you want to do really expensive GW kind of calculations at the state-of-the-art level, then of course you can saturate any computer. But most of the calculations can be done on a laptop. So certainly what you have there, if you have even a computer with several threads now, a good laptop can handle it. So for sure.
Yeah, I would like to add that also with GPUs, one of the advantages is also that you can have a lot of computer power for not that much money as well. So for example, in my machine, I have like a GPU. With one GPU, I can easily run like get a ground state, a DFT ground state for 100 atoms in 2 minutes or something like that. So there are a lot of things, and you can get GPUs like the ones designed for gaming that are not that expensive and allow you to do like give you a lot of computing power. So maybe we talk about supercomputers and stuff, but all these codes in general also work on like a single computer, and you can do calculations there. Maybe not huge things, but a lot of meaningful systems you can still do.
Wow. Javier, there is as a follow-up to that, a question by Omolulu in the chat, whether your code, whether ink is linear scaling.
No, it's not linear scaling. For the moment, it's just a standard plain wave DFT, like the same thing that Quantum Espresso implements, or like the standard cubic scaling DFT.
Okay. So then let's see, Omolulu, we have another follow-up. Do you want to ask yourself, or do you want me to read it to Javier?
Let me ask. So thanks a lot, for your talk. So do you know what causes your speed up to degrade after 32 GPUs? Is it
Sorry?
Do you know what causes your speed up to degrade after 32 GPUs?
This particular case, what happens is you start dividing. We're using state parallelization, so we take all the states and we start dividing them between processors.
Or between processors?
Yeah,
so
but the problem is, sorry?
So is the CPU that's slowing things down?
No, the CPU, we're not really using the CPU for anything. I mean, the CPUs, they're managing the GPU essentially. What is slowing things down is you start getting to a limit where you have very little number of states per processor.
Oh, okay, okay.
You just start dividing, and at the end, there is not much more to divide, so that's why the efficiency goes down.
Okay, so if you increase the size of your system, then this should go away.
Yes. In fact, yeah, if we take a larger system, yeah, it goes away.
Yeah. Okay. Thank you.
Okay. So let me see. I believe, Omolulu, all the other questions you asked earlier to Robert, that seems to be all answered, right? If I follow the chat correctly. Okay.
Yes.
All right.
Yes.
Okay.
Thank you, Robert.
Okay, great. So then we have a question by John to Robert, which I believe is not answered yet. And the question is, Robert, have you looked at using single precision for parts of the exact exchange, especially on GPUs?
Yeah, that's a good question, and yeah, certainly we have, right? Because just following along the discussion earlier, right? These calculations we're trying to make them possible, and then of course we're trying to make them more and more affordable, right? And so, like I was mentioning in the talk, right, we have a sort of three-pronged problem. One of them is that we're not computation bound, right? And we have a third communication, a third idling, and so for the computation front, even though we're only a third, I still want to hammer the computation as much as we can. So we have been looking at using single precision, especially so the computation burden is solving Poisson's equation for many pairs and on different domains. And so we are having some good luck solving Poisson's equation in single precision and then cleaning it up a little at the end with double precision. It has to be done a little more carefully than that, but yes, we are using those sort of ideas. We're also trying to do, preconditioning in the conjugate gradient. Again, there's some conflicts. Like so if you want to move to a GPU, right? You want to make it as much as a matrix multiplication, I think, as possible, and doing things like preconditioned conjugate gradient where you need forward and backward substitution is just a disaster, right? I mean, it's a disaster for CPU. A GPU is even worse, right? Because you have a lot of dependency and it's a much more serial aspect. So inverting is not a good idea. So we are looking into it. Thanks for the question.
And there's another follow-up from Javier, which is related not quite to the linear scaling, but whether you have benchmarked. So this question by Michel Coté, and the question is, have you benchmarked your code to other current DFT codes without naming any specific ones? Is it fast or not compared to other codes?
Yeah, well, I don't have problems naming, but yeah, the main comparison we did with Google, but in serial, and it was, I don't remember exact numbers, but Yeah, it was still faster. Both in the CPU and GPU version were faster than the keyboard code. I don't remember the exact numbers. I think that for the CPU was so. I think the GPU version of Ink, it was around 10 times faster than keyboard on a CPU. But it really depends on the size of the system and everything. So we haven't done a systematic comparison yet. We're working on that.
Okay. Okay, great. Any other question to any of the panelists, including John, I would say, because he's also here, so you can. Okay, Richard, go ahead, please.
Hello, I was just trying to type a message for John, but I'm too slow typing. So my question is, we've been talking about how us ordinary people can use the computer codes that we've heard about, but it must be even more how to use these big machines, these facilities. That's what I believe are the only places that these X-ray absorptions are done. How do you get started? How do you know what they're good for? How do you actually do something?
Are you talking about interacting with the experimental people at the big facilities?
Either interacting with them or at least interacting with experiments.
Great. Okay. Well, this is a very interesting question. Actually, the best way to do that is to talk with some of the beamline scientists at these facilities, because they actually can point an interested person to codes and so anyway, my suggestion is basically to find a colleague who's doing some experiments and interact with them.
So several people that are associated with USAfri are actually ones who do that. And it would be nice if everybody else knew who they were, even though we haven't been able to, do that explicitly at this workshop. Do you have good ideas, or maybe we could make a list?
Well, yeah, there are certain people. I mean, like we work with Matt Newville at Argonne, or Bruce Ravel at NSLS, or some others, Simon Bear at SLAC and SSRL. Anyway, one develops a kind of a set of go-to colleagues, and yeah, we should have a list of contacts. I think this is a great thing. Actually, Africa is starting to work on a synchrotron, and I think there will be opportunities then for many of the participants to participate in that. But it's a great collaboration between theory and experiment, and we need both.
Okay, we'll try to make it more easy to find on our website of who is interested in what, including this particular area.
Mm-hmm.
Okay.
That's very important. Thank you.
Okay.
And I also would like, I had one question for Georgies, which was whether your predictions for these van der Waals heterostructures, what experimental comparison do you have for those? Like, what is that hard to get, or what's the status of that? My apologies if you missed it.
Hello, yeah.
Missed it, but
okay, for the heterostructures, I think they are not synthesized yet. The Janus and this transition metal dichalcogen zinc oxide. So we are comparing first when we do the individual monolayers, we compare it with the experimental results, and we have seen we are going in the right direction. After that, we prepare the heterostructure, and then we take the results as it is. So no experimental data for the heterostructure.
And do you have any colleagues that you are currently working with, that you're planning to work with on that experimental part?
No, we have recently started a collaboration with Elizabeth from UC Berkeley, She's also doing the computational work. So I am trying to widen my groups, and maybe in the future we will try to find someone who can collaborate with us for the experimental work.
Okay.
Okay, thank you.
Great, thank you.
Thank you.
Any other questions? Unless I'm mistaken, I think we are caught up on all the questions in the chat, and I don't think I see any raised hands currently. Let me see real quick here. Yeah, looks good to me. Any other question to anyone? All right. So the silence after asking this question, the conference room is
hello.
Okay, Dick, yes, go ahead.
Yeah, my second question to Prof. John. So he didn't respond. So it was is the green functions method can deal with a multiplex effect?
Does the Green's function method capture
deal with multiplex effect?
Multiplex effects. Okay, John, maybe you can comment on that.
The multiplet effects require a kind of a CI type initial Green's function. We're working on that. I'd rather not really discuss it because we haven't figured it out completely, but stay tuned. It should be possible, but you need a CI or something like that starting point. And
Okay. Great. So I think in that case, what I'll probably do, we already missed the break. So what I'll do is I'll probably send you guys into the breakout rooms. We have 5 breakout rooms, 1 for each speaker. And you guys, please feel free to join those breakout rooms. You can meet and greet the speakers and chat with them a little more. That would be until 8:10 a.m. Pacific, 10:10 a.m. Central, and 5:10 p.m. Kigali time. And then we have another break, and then we'll go directly into the poster session. There are no other comments. Thank you so much for presenting and for showing up.
Thank you, Andre.
Thanks to all the speakers. That's right. We should clap here again. Hold on a sec. Here we go. Virtual clap. Okay. Thank you.
Hi, everybody. It's Amy. Just a reminder that this time is for the invited speakers. We'll be having the posters after in about half an hour. So right now it's your time to have a chat with the invited speakers of the day. Richard, we have about 10 more minutes for this informal meet and greet time, and then we'll have a break. So I'll get people back at about, it's going to be 8:15 your time.
Hello.
Hey, Gamaches?
Hello. Good morning.
Yes.
Yeah. So today is the last day, right?
Hello, Ami.
Oh, yes, Dick Hartman?
Hello?
Hello.
Yes, Dick Hartman, I can hear you, and Gamaches, I can hear you.
So
Do you hear
are
me?
you hearing me now, right?
Just a moment, Dick. Yeah, Dick
Hello.
Hartman, I can hear you. I can hear you, Dick. We put it in the. Hang on, Gamaches. I think Dick has some troubles.
Okay, are you hearing me now?
Gamaches, I still hear the flutter on your mic. Dick Hartman, let me send him a message.
Okay. Yeah, I can see. I can see. Yeah, I can see Ami.
Yes, I said I want to move to John's room. I have some
John Rehr's room. Let me move you over there. Okay.
to him. So if because I'm using actually an old version of
Okay. I put you there. Let's see if you go there.
Hello, Ami.
Yes, Camaches?
So I want to talk Henry. So what shall I do?
Oh, I would say just wait until the poster sessions, because I know that since Andre was hosting this morning, he went to get something to drink. So yeah, he's probably getting a cup of tea. So he'll be back in a bit. Yeah. So I would just wait until poster sessions, probably about 10:15 or so. Your sound was better when you adjusted it kind of with your microphone. So I think maybe the cable is a little bit cannot your sound cable is maybe not connected. Okay. So that's why I keep muting you, because it makes this fluttery noise.
Understand.
Okay.
Yeah.
Okay.
Thank you.
Okay, Gamachis, I'm going to mute you now.
Okay. Hello, Richard. Hello, Richard.
Unmute. Yes. Hello.
Hello, good morning.
Good morning to you. I'm trying to wake up.
Yeah.
Even though I've been on a couple of hours, I'm still waking up.
Okay. Yeah. So today the end, yes, the end of the workshop, right?
Hold on a minute. I couldn't hear what you said.
Today is the end of the workshop, right?
Okay. Now I turned up my volume. Yes, today is
the last day, right?
Yes.
Yeah. So I don't know how to. Is that possible to know how many people are now participating, and so we can contact with each other even within Africa?
Well, let's see. I don't know exactly how we're going to try to summarize and give information about who's actually been involved, but we'll really try. And there's at this Amy is going to send out a survey form, and we want everybody to participate, and then we'll get more feedback to you, and the more feedback to us that you can give, the better. Okay, so one way or another, there'll be a list of everybody involved with enough of a few words about their interest to help everyone. Okay, thanks for questions. We need it. John, if you're speaking, I can't hear you. You're muted.
Thank you. Somehow something happened and I became muted.
Yes.
As I was saying, the answer was yes, you need both emission spectrum and absorption spectrum. I hope that answers your question.
Yes, thank you, it does. I'll send you in the chat my email address and you can just send me the reference, or I'll email you.
Email me is best.
Yeah,
that would be good.
Thank you.
Happy to respond. Yes, in fact, that was a very good question because people want to use RIX. RIX is a great technique because it avoids the core hole broadening issue and gets very accurate results for excitations.
So since I have a moment, I'm just curious, RIX has also become a competitor with neutron scattering and neutron spectra calculations as well. I don't know all the details. I'm more used to working with neutron scattering data since I do frustrated magnetism primarily and correlated systems. Can your method as well be extended? It's neutrons as opposed to electromagnetic radiation? Would it be possible? I'm just curious.
I'll have to think about that. Sorry, I don't have an instant answer. Send me an email, please.
Okay, thank you. Yep, I will.
I promise to think about it.
I'm not sure if everyone on here even tuned in early enough to understand what RIX is. Did I miss it, or did you start in the middle?
I think it was his question. Can the techniques that I mentioned be used to interpret spectra like RIX? And my answer was that RIX is essentially a way to measure losses in, photon out spectra. And they can be calculated and interpreted using a convolution between an emission spectrum, an absorption spectrum, and a resonant denominator. There's an approximate formula that's simpler than the Kramers-Heisenberg formula. And so that can be used to both calculate and interpret RIX.
So maybe I can insert just a word for us people not experts. It's like Raman scattering, right?
Yes, it's like Raman. It's losses.
And somehow the resolution has gotten so good in recent years that you can use X-rays and detect energy differences that are like photon energies.
Yeah, that's correct. It's because you avoid that core hole lifetime broadening that's intrinsic, and instead get a much smaller broadening. I don't know if it's probably comparable to some phonon broadening. Yes.
But you can measure phonon energies and magnon energies without neutrons and to incredible accuracy.
Yeah, pretty good accuracy. What is it?
Okay, fine. I exaggerated.
Yeah. Okay. So tenths or hundredths of an EV. So it's pretty good. Yeah, that is incredible, isn't it?
Yeah.
I think more code should try to calculate RIX, actually. It's an important spectroscopy development. And in fact, we have to really thank the experimentalists. They're always coming up with new experimental techniques which push the theory to now higher and higher accuracy.
Okay. Well, I emphasize phonons. It's just because for me that's just so amazing that it can be done. But I think I inserted maybe too much. That really the electron spectra is most interesting and probably what you would focus on.
Actually, the phonons are really increasingly important. Also, eels can now get very high resolution too.
Oh yeah. So, electron energy loss.
All these experimental techniques drive the theory and push us to higher and higher accuracy. By the way, you can get a cumulant for the phonons as well, so you can see these very fine energy differences.
Okay.
Richard, can you hear me okay?
Yes.
Okay, I think we should go ahead and start the concluding remarks, and then will run the posters, contributed posters. It's time.
Okay. I was wondering who was going to tell us it's time to do that. So is Omololu and everybody else on?
Yes, but Renata had to catch her travels.
Right.
So I have her remarks ready.
Okay. I think Omololu was going to go first, and I guess you can get everybody back into the meeting.
Everybody's here. Yeah, everybody's here. I closed all the poster rooms.
Oh, okay. Okay, is Omololu on?
Yes, I'm here, Richard. Hi.
Okay.
I don't know. Oh, sorry. Let me start my video. So then you should see. Okay. Sorry. Okay, can you hear me now?
Yes.
Yes.
Okay. So I will start simply by saying thank you to everybody. So we started the workshop on Monday, and it's been a tedious one. So I would like to thank all the speakers who contributed from Monday up to now. So we have roughly like 25 speakers, the keynote speakers together with the invited speakers, about 25 people. And then also some of you sent in videos that you pre-recorded. So we really like to thank you for all the efforts that you put into it. Also, I mean, in March, we had a small kickoff. Many of you also sent in videos. So to all the speakers, the chairs of the session, I would like to say thank you on behalf of Richard, Steve, Renata, Shinyad, and Amy. So we thank you all for being part of this USAfrI initiative, and we hope to continue throughout the year and next year and even beyond. Thank you very much.
Okay. Amy? Oh, sorry. Sinead, right.
Okay, so just a few more official thanks. So this program, as we've mentioned a few times, is supported by the American Physical Society's Innovation Fund. And so these are awards that are given for APS mission focused projects. So we've been lucky to get support from them in their first inaugural award, and they've allowed us also to extend it due to COVID circumstances. And then all of these other strategic organizations that we've been partnering with. So, you know, importantly, the ICTP in East Africa, where Omo is the director, and then some more organizations both in the US and in Africa. So some planning steps ahead. We are going to be setting up an advisory panel to plan for the next workshop and for helping us arrange the planned visits, the planned research stays for African scientists visiting the US. Also, we will have part of the advisory panel will be to help with fundraising for the next round as well. So if you think you'd be good at this, then please let us know and drop us an email. We have some ideas anyway of who we'd like to be on the advisory panel, but please let us know if this is something you'd like to be involved with. And then a very final thanks to Amy Young, who you all know very well at this stage from the week, and to Steve Ndenge from the ICTP in East Africa, who have really pulled off a pretty Herculean task this week in getting this all together. Okay, I think I'm passing it over to you, Richard, I think. Now.
I believe Renata is going to be next. Is that right? I can go if it would be better.
Richard, I'm going to play the remarks from Renata. And
Good.
Gamachis, I'm going to keep muting you because I can.
Hello, everyone. When Amy plays this recording, I will be on the road. I want to tell you about the plans we made in 2019 for the second USAfri workshop. Several conferences are already happening in hybrid mode, and our workshop will likely be in that format as well. The plan was to have the workshop at Columbia University in New York City, a major port of entry on the East Coast of the US. The workshop should be on the Morningside campus in the Upper West Side of Manhattan. Here is a view of the campus looking south. It's within walking distance from Central Park and the Hudson River, but far from Lower Manhattan and other more touristic places. It's approximately 2 hours by car from Brookhaven National Laboratory. If you are familiar with the map of Manhattan, here's the campus on the Upper West Side, but more relevant is where the event should happen. Now, here looking west, you see the campus, the Davis Auditorium, and here's Renata's office, and here's the International House, where the visitors will stay within walking distance. It's a very special place and has been designated a New York City landmark. It's a welcoming place for international scholars with comfortable accommodations and event spaces. It was the first of a series of iHouses in the US. iHouse in Berkeley on Piedmont Avenue, where I lived for 2 years. They all belong to this International House Organization, a nonprofit, independent organization that works with universities. Columbia is reopening in the fall, but requiring everyone to be vaccinated. The iHouse is not accepting reservations at the moment, but they hope to start in the fall. Therefore, the plans are not 100% certain yet. This iHouse issue is still pending. It will be an extremely important event for us, and we need to prepare. There is work to be done, establish topics for collaborations, plan for the visits after the workshops, fundraise, etc. Richard will expand on this. So let me finish here by thanking immensely, infinitely, Amy Young and Steve Indengen. They were the ones here every day, an hour, working and making this workshop possible. And of course, the APS Innovation Fund, that is supporting this workshop series, the APS Division of Computational Physics that incremented the Innovation Fund Award and made possible our mini workshop in the APS March meeting, and the University of Illinois at Urbana-Champaign that has provided funds for admin support. So long, everyone. We'll see each other again soon.
Fabulous. Okay, so I have the pleasure of going next. Let's see if I can share my screen. Okay. Okay. Everybody else knows how to do this better than I do, so great. It really is exciting to be part of something really new. This hasn't happened before. It builds on top of the things that we have done before, in like the assessment in Africa, and it brings in whole new aspects. Because of USAfri and electronic communications, there are now great opportunities for collaborations. And the challenge to you is to use what you learned here. And remember that posters and talks are recorded online, so you don't have to depend on exactly your memory to identify potential connections and collaborations. It's not hard to do this. There are a lot of good, friendly people, remember, a lot of friendly faces on each continent that are ready and willing and happy to answer questions and enter conversations. The peer program is another way that you can be involved. Sign up on the website. Renata has just given the introduction and welcome for the 2022 2022 workshop. So the thing I would like to emphasize is that only a limited number of people can be supported for travel. So be active. Participants are chosen based on the progress following this workshop. So once again, I'd like to just re-emphasize your challenge. Starting now, before the summer of 2022, most important is to do good work and problems you're interested in. Maybe you've picked up something else that you're interested in at this workshop, or maybe you already have the interest, but focusing on doing good work is the main thing. And it can help if you identify people with the same or complementary interest and initiate discussions, look for collaborations. That's the idea for going into the future. So there's some other events that good to let you know about and for you to participate in, like the 33rd workshop. This is an ongoing series that happens every year in the United States on recent developments in electronic structure methods and applications. So it's happening in July this year, and it's a virtual workshop, and the registration is open to everyone with no fees. The deadline for posters is coming up very soon, June 21st. Here's the website, and you can also get it by going to the USAfri website, which has a link. So there'll be other things listed on the USAfri events and on the websites, and things that will be the new developments for USAfri itself. So next, Amy is going to send out messages with getting you to fill out a feedback form. This is important. This is not like your standard thing that people would say, oh, did you enjoy the meeting? What did you do this or that? And only a very few people participate. This is a time when we need your feedback and your suggestions for USAfri to really continue and do well, and to show you're interested in continuing participation in USAfri. So thank you, and it's just wonderful to be with you for this workshop. And don't leave, there's posters coming up. We just wanted to get this done before we have the posters, and so don't leave at this point, stay around for the posters. That's it.
Okay, Richard. So I just wanted to, I'm going to switch to gallery view. We have some people who joined after the first morning talks. So I'm going to take a couple more screen captures and stitch them all together to make a photo, a group photo of sorts. So I'm going to ask everybody to turn off your camera, turn on your cameras, and I'm going to, let's see. I'm going to stop sharing your screen, Richard. Okay, great. So we did this before, and I apologize for those who have to do this 1 million times, but that's what I do. Yeah. Okay. All right. So I see Dick Hartman. Can you smile, please, Dick Hartman? Nice. Okay. Thank you. Robert Stasio. Das looks very pensive. Okay, that's less pensive. Good. Edward, you look very serious. Mr. Okay, thank you. Mark Peterson looks happy. Let's see. Nipa's still smiling. John is still smiling. Let's see. Michelle Cote looks happy.
We don't see Amy. We don't see Amy.
Okay. I will Photoshop myself in later. I see Sunday. Jonah is there. I see Tim. He looks like a radio star. I see Veronique. There's Veronique. Very nice. Okay, here's Rosmael. Rosmael looks very serious. She's been working very hard. Okay. Perpetua also looks very serious. Hi, Perpetua. Nice. Okay. Alika, I put your video in today. Zara Hushmand. Let's see who I see. Christian again. He is Asnake. You look very serious. Too serious. Okay, good. Machis. Okay. And then Oleg Benga, you look very good. And Victor, I see you. And let's see, do we have everybody? I think I have a very nice photo of everybody. Yes, Gauru, I have you from before. Steve, yes, Matthew. Okay, perfect. So now what I'll do, I put the link for the short link for the survey in the chat. I will also just send out an email wrap up today. So that will include a list of participants because we had some new people coming on and off every day and I wanted to modify. Oh, Baba Femi, can I have a smile from Baba Femi? Nice, okay, very good, thank you. Yes, so I'm going to play the poster videos next. And we had some more. And again, as with everyone else, I really appreciate all of you who took time to make them. And some of you also recorded with me, and I really appreciate that. Although Fru isn't here quite yet, but he is, his group is having poster work also. So let me cue up that video.
So we can stop smiling now?
You may stop smiling and look like serious researchers once again.
Okay,
yes.
Thanks so much.
Actually, I didn't share my screen. I was going to make the joke, mostly because I don't have one on this computer, but my haircut was administered by a physicist who's German. So he likes precision, but he's theoretical. So he can compute probably a better haircut than he can actually execute. Yes. So yeah, I'll Photoshop myself in maybe after we fix my haircut.
Good.
Okay. Yeah. All right. So let me share the screen and great. All right.
Hello, my name is Rehr Gashua. I am from Addis Ababa University. I'm a first-year master's student. So far, I've been working on a classical molecular dynamics simulation using a LAMPS simulation package. So I did a zirconium 50, niobium 50 solidification. And also I have did some Monte Carlo simulations on particle sedimentations and adsorptions. And now currently I'm working on this asset team in Addis Ababa University, which is now got some computational facilities via this USAfrI initiative. So we have been working on 2D materials and also lithium batteries, specifically when we say 2D materials, 2D bulk heterojunctions for battery and solar cell applications. And while I'm now a master's student, for the future, I want to work on a machine learning approach for computational materials discovery. And also I would like to have some opportunities in the coming futures. And I thank you very much for this opportunity.
This is Elka Obulu from Catholic University of East Africa. Currently, we are working on the structural and electronic properties of antiperovskites as they are applied largely in various fields.
My name is Olivier Gingras, so I'm a PhD student in Montreal at the University of Montreal. I'm in the group of Michel Côté and André-Marie Tremblay, and I'm studying first principle approach to correlated materials. So I'm using DFT plus DMFT to simulate some strongly correlated materials. And my focus has been on unconventional superconductors where the superconductivity emerged from spin and charge fluctuations. And most precisely, I've been focusing on strontium ruthenate, which is thought to be, which is kind of an archetype superconductor. I'm finishing my PhD, so I'm going to the Flatiron next September. And so I'll be there at the next meeting of electronic structure meeting at the Flatiron. So I guess a lot of people from this meeting will be there also. So it's going to be a pleasure to meet you there as well.
Hello, I'm Habib Josué Manyungu. I'm from Mayengwabi University to Brazzaville, Congo. I'm using quantum espresso for my calculation. Thank you.
Hi everyone, my name is Masfundiro. Currently, I'm a PhD student at Addis Ababa University under the supervision of Dr. Yedilfana Satarge and Dr. Charanet Amente. We are working on new organic material discovery for redox flow battery applications using machine learning. Our method first encodes discrete molecular representations into continuous lower dimensional vector called latent space using variational autoencoder. It is a deep learning algorithm that has encoder and decoder compartments for the purpose. This continuous latent space helps us to predict electrochemical property like redox potential, solubility, and stability. Furthermore, the latent space is used as an input in our generative model called GAN for inverse design approach. GAN is an abbreviation for Generative Adversarial Network that has two parts called generator and discriminator. The generator takes random samples from latent space using Gaussian distribution and fixed desired property to create a new molecule. However, the discriminator labels the generated molecule as real or fake. Generally, it is a zero-sum game that the generator wants to minimize as the discriminator maximizes. Our work is in progress and we are happy to have collaboration from USAfri initiatives. Thank you for your attention.
Good morning to all. My name is Njoman Christian May, a PhD student with Material Science Lab, Department of Physics, Faculty of Science, University of Yaoundé 1 in Cameroon. I work on nanomedicine, targeted delivery, and nanoelectronic device with density functional theory. I work with a group here in Cameroon. I work to extend our work and for experimental aspect. Thanks for your listening.
Hi, I am Kauthar Saleh, PhD student from the University of Tunis al-Manar under the leadership of Professor Ali Ben Ali. We work in collaboration with Professor Erik Hickelman and Dr. Anas Abdul Wahab from Leibniz University Hanover in Germany and Professor Richard Skeletor from University of California. In my poster, I present some results of our work. Using the Demergy method, we investigate the Hubbard Hamiltonian on ladders where the numbers of sides per rank alternates between 2 and 3. We show here the existence of Lagrange ferrimagnetism order in the one-dimensional ladder geometries. Our work provides detailed quantitative results which complement the general theorem of Leibniz for generalized bipartite lattice. Thank you.
Okay, so those are today's video introductions. I still encourage, if you haven't made one, please make one and send it to me and we'll put it on the website. And if you see have any corrections for your poster title, links, or talk titles, or any affiliations, please let me know before I put together the participant list. I'll be working on that today and I'll probably send it out over the weekend. So thank you, everybody. And I'm going to open the breakout rooms now. Oh, I forgot to mention the talks will be on YouTube and as well, and I'll link to those when they're ready. They just take some time to encode and I need to, tidy them up a little bit. So those are the main things: participant list, talks, videos, and poster sessions and corrections. So I wish you all a good rest of the breakout session. We're going to leave them open. So as long as there's somebody in the rooms having discussions, we'll keep the rooms open. So don't feel any pressure to finish at any specific time today. And we're all very, very happy to see you all. And thank you so much for participating. Yeah, thank you so much. Yeah. Okay, great. All right, I'm going to open the break rooms.
Hi, John. I just thought I'd say a quick hello. I'm in the hallway between two posters, and I enjoyed your talk. And I'm not sure if you're there, but I was glad to hear you talking a little bit about interface between DFT and more CI-like efforts. So it's been a really enjoyable conference. Hope to talk to you soon. So I think you're not there. So anyways.